Hello, welcome to Basics of Finite Element Analysis course. This is the third week of this course, and we will start this week with a discussion on variation, the concept of variation and variational symbol. And once we are done with it, then we will start with figuring out details of weak formulation and different variational methods used in this particular context. So, we will discuss variations, and I will again explain this by an example, and then we will develop some mathematics around it. So, suppose I have two fixed points, points A and B. So, A and B are fixed, and between these 2 points there is a rope, somewhat better rope. So, this is a rope which is hanging due to its weight. Okay. And we have discussed, let us say that we are interested in finding the length of this rope, So, that will be, let us call it length, and if this is my x axis and this is my y axis, then length is equal to integral. So, this is x is equal to 0, this is x is equal to x a, integral of x to x a 1 plus dy over dx whole square root times dx. I mean, this is the relation we had explained earlier, right. So, this I called in my earlier lecture as I of, and I can replace this dy over dx. So, suppose I call u, which is the deflection of the rope at any point. So, u depends on x. So, I can call it as u prime square. So, this is I, which is a functional, and it depends on u. It depends on u. It depends on the shape of the rope. If the shape, now it is hanging because of its own weight, so it has a certain thing, but depending on the shape of the rope, the length of the rope is going to change. Now, think about it, that suppose I am looking at some point, let us say I am looking at this point P. So, but before I go there, I will rewrite this, that I of u is equal to integral of 0 to x a, and what is its, I call this some function, this thing f of x u prime. So, now I just made it more general. Okay. So, this we have done in the last lecture. So, there is nothing new about it. Now, we are looking at this function f closely. Okay. So, now consider that at point P, and at point P x is fixed, x is not changing, So, at point P I disturb the rope by a small amount. So, okay, I disturb the rope, and because of that disturbance, initially the deflection was u, and it changed by a small, it varied by a small amount. So, the new deflection of the rope is u plus small variation, and I represent that variation as delta u, this Greek letter delta small times u. So, and remember this is at a point P where x is, so x is not changing, x is not changing, and I can disturb it in all sorts of ways. So, I can similarly disturb all points on the rope in all sorts of ways. In one set of displacements could be, I can disturb it like this. So, I am disturbing it about with reference to the original configuration. Okay. So, this is one variation, this blue line. I can disturb it like this. So, now I have amplified it, right. This could be another disturbance. Okay. So, but the point is that I am disturbing it at a point P where x is fixed, and the nature of this disturbance could be anything. The only constraint which I have to impose when I am making this disturbance is that at A and B it cannot violate the boundary conditions. Okay. That is very important. So, these variations have to subscribe to fixed BCs related to u at points A and B. Okay. This is important, that they have to subscribe to fixed. So, here the condition at A was 0, u is 0, and at B also the value of u is 0. So, what will be the variation of u at A? It will be 0, it can never be non-zero. It can be non-zero at all other points, but it cannot be non-zero at A and it cannot be non-zero at B, because my boundary condition is like that the variation cannot violate those boundary conditions. Okay. So, this is important to understand. So, I say that delta u represents what? The variation, and I can express this delta u as some constant number alpha times a function of x, which is Vf x. Now, this V could be anything as long as it is consistent with the boundary conditions, and it is not any boundary condition. Suppose I have a force here F, this V does not depend on the nature of this force related boundary condition, agreed, but it will depend on the boundary condition which relates to u. Suppose instead of having a fixed situation here at point B instead of having a fixed situation, I am applying some force there. Suppose it is not rigidly fixed. In that case, there could be variation at B, okay? There could be variation at B, but if B is fixed, then there cannot be variation. They are two different things. You have to understand this, they are slightly two different things. Okay. So, it depends on boundary conditions which directly relate to u, okay, which directly relate to u, at least in this kind of context. So, our choice of V can be general, and the only restriction is that BC is related to fixed values of u at A and B must be respected. You cannot break those boundary conditions. This is very important to understand. Third point, so first point is variation at A and B in this case is 0 because the value of u is going to be 0. That is the first thing. Second thing is, suppose at point B I remove the boundary condition that u is 0 and instead I am holding it by some hand, okay, I am holding it by hand. So, I am applying some force, then in that case variation could be non-zero at point B, right, And the third condition is that variation at A and B will still be 0 even if the value of displacement at A and B is known but non-zero. What do I mean? Suppose the displacement at B is 5 millimeters, displacement at A is 0, that we have, and displacement at B is 5 millimeters, but it is fixed. I take the rope at point B and I move it 5 millimeters upwards and I fix it there. So, displacement is 5 millimeters, but what will be the variation at that point? Is any variation possible at point B? I have fixed it at that point. So, there is no variation possible at point B. Okay. Variation can happen only if my boundary condition permits me to have that variation. So, in this case I have moved the point B 5 millimeters upwards and I have fixed it there. So, no variation is permissible at that place also. Okay. If it was just the case of force, my hand could move up and down. In case I was just lifting the rope with hand, my hand could move up and down. The force is being applied, but my hand could, so variation would have been possible. But in this case, I have moved my rope by 5 millimeters up and I have fixed it. So, say I have glued it or bonded it or rigidly held, now I am holding it. So, no variation is possible. So, the third point is, and this is a next level, another fine point, that if A at point A, U is prescribed, it does not necessarily have to be 0, but if U is prescribed, then variation at U is not possible. Similarly, if U is prescribed at B, then variation at B is not possible, and so on and so forth. At all other points in between A and B, U is not prescribed. So, variation is possible. And what kind of variation is possible? Any variation is possible. So, I am not restricting V. Any variation is possible. Variations are not possible only where U is explicitly prescribed. It can be 0, it can be non-zero. But if it is prescribed, then variation will be 0. This is very important to understand. Fourth thing, I want in general that these variations, and we will see it later, why we want this, we want that the amplitude of these variations should be extremely small. Okay. The amplitude of these variations should be extremely small. What is extremely small? I mean extremely small. So, I do that by controlling this parameter alpha. I can make this alpha as small as possible. I can give a parabolic variation, but I can make the amplitude of that parabolic variation extremely small by controlling this parameter alpha. I can give this this variation in blue color, but the amplitude of this variation can be very small by picking up the right number, and I actually make it infinitesimally small. We will see it later. Okay. So, that is the importance of this parameter alpha. That is the importance of this parameter alpha. So, the variation in U is designated as delta U. It can be represented, so this is designated as delta U. It can be represented by any function Vx as long as this function V is consistent with the boundary conditions related to U in this case, right. And the amplitude of these variations is, we try to make it as small as possible by picking up some number alpha which is extremely small. Understood? So, this is what is known as variation. This is what is known as variation. Give another example. So, suppose I have a beam, okay, and let us say this is my neutral axis of the beam, the midline, mid plane of the beam, and I apply a force F I apply a force here. Okay. Then because of this, the neutral axis of the beam deflects by some amount. Okay. And let us say I look at a point P, and let us say the deflection of this point P is point P is u of x. I mean, typically we use the term w, here I am using u of x. Okay. So, now I am interested in figuring out the variation on u of x. So, I will say variation in u of x is what? It could be any function, right? It could be any function v of x multiplied by a parameter alpha, but this v has to be consistent with BCs related to u and u prime and so on and so forth. Okay. So, now we have to see what kind of functions we can choose. What are those restrictions? We know that at x is equal to 0, what is the value of u? 0. So, what will be the variation of u at x is equal to 0? 0. Also at x is equal to 0, what is the slope? Slope is 0, it is a fixed cantilever, which means the slope of the variation also should be 0. This means v of x at 0 should be 0, and this means v of x prime at x is equal to 0 should be 0. Okay. Is there any boundary condition here at, so suppose this is x is equal to x, so let us say this is x is equal to L. So, any such boundary condition is needed at the free end? Is there any restriction on choice of which is dictated by the conditions at the free end? It is not a free end, there is a force there, there is no, right. So, the variation could be non-zero at the other end. I will not call it free end because there is a force being applied, right. So, there is a force being applied. So, this is there. So, we will pick one or two functions to see what kind of functions we can pick. One function could be some possible choices for v of x. V represents the shape of the variation, V represents the shape of the variation, and alpha represents its amplitude. So, some choices, so v of x could be a1 x square plus a2 x cube plus a3 x4, this could be one choice, right. At x is equal to 0, does it meet our condition? At x is equal to 0, v should be 0, it meets our condition, and it should meet the other condition also. Its derivative should be 0 at x is equal to 0, it meets the condition. So, this is okay. Let us look at another function, v of x is equal to sine of x. Does it meet the first condition? It meets the first condition. Does it meet the second condition? Yes or no? It does not meet the second condition, because the derivative is cosine of x, so it is not okay. So, you have to be careful what kind of functions you choose. Okay. So, that is there. One more function, a1 times 1 minus e to the power of x square plus a2 1 minus e to the power of x cube. Okay. This is the third function, some possible. So, this is not okay, this is okay. What about this guy, third function? At x is equal to 0, it is v is 0 or v is not 0? It is 0. At x is equal to 0, is its derivative 0? 0. So, this is also okay. So, this is an acceptable function for representing the variation. Okay. So, these are so this is an overview of the variation in the system. So, again I will summarize this whole thing, that the first thing is that when we are picking up variational functions, so what we have seen is that we have developed an approach through which we can depict variations in the function u. You could represent something physical, for instance deflection of a beam or temperature, and we have figured out that how do we correctly choose the variational functions related to maybe a function u or v or w, whatever. And the only restriction which is required, at least at this stage we are going to describe, is that the variation should be of a nature so that the boundary conditions associated with the variable u and its derivatives, if needed, are not violated. If we do not violate these boundary conditions, then our choice of the variation is appropriate. Next thing, earlier we had seen that f is dependent on u and its derivatives and so on and so forth, right. So, if u is changing, if there is a variation in u, then there will be a variation in f also. Okay. So, that variation in f which occurs due to variation in u, which occurs, is known as variation of f, and it is designated like this. Okay. And this I can calculate it how? So, suppose f is depends on x, u and u prime, f depends on x, u and u prime. Then the variation in f is this is the mathematical thing. How do I calculate the total variation in f? First I change x by a small amount and see the variation in f, and I measure that number. Then I change u by a small amount and I again measure the change. So, these are those individual variations ascribable to changes only in x, changes only in u, changes only in u prime. But this term is 0, change in x. Why? Because when we were discussing variations, what did we say? That we are looking variations at a given point, right. So, this equation is very similar to the equation df is equal to del f over del x delta x, like that. But this term does not exist when we are talking about variations. This is important to understand. So, variation in f is equal to partial of f with respect to u times variation in u plus partial of f with respect to u prime times variation in u prime and so on and so forth. But the x related term does not come. So, this is an important equation and we will use this relation very frequently when we do finite element formulations. Then we will also write down a few other laws that suppose related to variations. Then if there are two functions f1 and f2 and I have to calculate the variation of in their products, then very similar to the way we do for differential calculus, it is nothing but f2 times variation in f1 plus f1 times variation in f2. Similarly, variation in f1 over f2 is equal to variation in f1 divided by f2 minus variation in f2 divided by f2 square times f1. This is the rule which is very similar to that which we use for derivatives. And if I have f1 to the power of n, then the variation in that is nothing but n f1 n minus 1 times variation of f1. And the last and very important relation is that suppose I have a function and I take its variation and then I differentiate the variation. So, d over dx. So, what am I doing? In this case, what I am doing is I am having a function u, I pick up an appropriate variation which is consistent with boundary conditions directly related to u, and then I am differentiating that function. So, this is equal to d over dx, and what is variation of u? It has a shape associated with function v and an amplitude, right. This v could be anything as long as it is consistent with boundary conditions. So, I am trying to figure out how do I so my goal is how to calculate this thing. So, this is equal to alpha dv over dx is equal to alpha times v prime is equal to, now what is v prime? Alpha times v prime is what? This is nothing but variation in u prime, right, and this is equal to dx. So, I can write it that d over dx is equal to variation in du over dx. Which means that d by dx, see d by dx is an mathematical operator and variation, this is also an operator, it is an operator, right, are commutative. So, either you do variation and then take the differential, or you take the differential and then take the variation, you will end up with the same answer. So, they are commutative. So, depending upon your ease, you can do this first and do that later, or vice versa. So, this completes our discussion on variations, and starting tomorrow we will start discussing weighted integral, weak formulations and all, all the stuff related to this broad theme of topic. Thank you very much.